I'm going to talk in this video about a common error when making phase plots with real eigenvalues. I'm specifically focusing on sources and sinks, so ones where this e to the has both a positive or a negative, right? Saddles are a little bit different and I think a little bit easier than doing some of these sources and sinks. So take a look here. I've got this vector, which is green on both of these, and this vector, which is purple on both of these. This one has an e to the t, and this one has an e to the 3t. So notice I put a 1 and a 1 and a 3 and a 3. Same thing over here. Um, this phase plot here is what people will frequently do that is not correct. And I'm going to try to explain why this can't be correct and why this has to be correct. Part of the issue here with this one is that these things hook back in to that purple vector. Once they go out along the parallel with the green vector here, they can't go backwards on that. And I'm going to try to show you why. And I'm also going to try to show you why once they go out and they change directions, then they go parallel to the larger vector, or the larger, the vector with the larger exponential value. So key here really is two things. One, recognizing that this is all t values that we're considering. So t equal to 0 for this spot right here might be here, right? So we're considering positive and negative t values for this. Maybe we know that at t equals 0, this is a trajectory of something, right? So maybe we know at t equal to 0, this piece was at negative 3, 3. Well, as t increases, it goes out this way. If I want to figure out what happened before it was at that spot, that would be a negative time, so that would take me back to here, right? So contextually, it can make sense to have a negative t value, and these phase plots always include negative t values. So in order to look at this, we are going to flip over to a graph that has both e to the t and e to the 3t graphed on it. So notice here I've got e to the x, or e to the t, whatever you want to think about it as, and e to the 3x. So e to the x is blue, and e to the 3x is red. When I graph them, and I've already gotten a window that works well for me here, notice the blue one, which over here is e to the x, that one is bigger before t equal to 0. And the red one is smaller. And then at t equal to 0, they cross, right? So at t equal to 0, this 3t one begins to take over. It gets bigger. And the 1t one, the e to the x, e to the t, is smaller. So initially, the e to the x is bigger. And then after t equals 0, the e to the 3x is bigger. So that shows up on our phase plot. When we come to the phase plot, it's going to follow, when I've got those negative t values, those trajectories are going to follow that e to the t. Maybe I should have done these color codings the same way as I did on the graph over there. Maybe I'll switch it in a moment. But this right here, this green, this e to the t, is bigger initially, and then this one begins to take over, because that's how exponential functions work. So I did switch the colors just so look, purple small, green big, and then it flips. Purple big, it's closest to purple I could get. Green smaller, right? So if I flip over to the graph, remember it's green, and then that's why initially I follow the green, and then afterwards we follow the purple. So I think you should at least be convinced that we're going to follow green and then purple next. Then the next question becomes, why do we why do we not go back in? Why do we not get this hook back in? Well, think about it. We have already grown, or this trajectory has already grown. If I'm looking at this line right here, this trajectory has already grown along this vector, when I'm going to, along this green vector. The green vector doesn't go away, it just stops growing as fast as the 3 vector, right? So if I were to go like this and then go back in, then that would be representative of a shrink or a decay of some sort along the 1, along the green. What we know about an exponential function is that this green continues to grow. So it does continue to grow. It doesn't go down. I would have to have this graph turn and go back down in order to get that hooking action back in towards the purple vector on my phase plots. This hook action here that people tend to put on these phase plots when they're first learning how to do it, it's impossible. It doesn't make any sense. So I think we've got 2 things at this point. We're going to follow the green first because of when things are bigger than the other, and we consider t's that are negative and positive, and we don't get this hooking action. The next real issue is like, all right, why do we actually go parallel to this 3 instead of like going on, along the 3, but also out along the 1? And that has to do with what the effect of this 3 versus not having the 3, what effect that has on the graph. And I'm going to go back to the graph. I'm working with this window right here. You can't really see it as much, right? This thing clearly gets bigger, but that guy's getting big too, right? The green one's getting big too. So shouldn't we sort of go along both? Well, watch what happens if I make my window, my Y Y window bigger. I'm just going to go up to 100. Oops, need another 0 graph. All right, so look here. There's the green one, but look at the purple one. It explodes, right? So the green one is still going up, but this thing goes up so much faster, and that's because of derivatives and calculus and exponential functions. But that's why we then, as in terms of growth along these phase plots, the green one isn't growing as much. It's not as dominant. This thing takes over, and the green becomes inconsequential as t values get big. So that's why we follow this one as t gets big. So hopefully I've addressed 3 things. 1, we definitely initially follow the green and then we follow the purple. 2, we don't get this hooking action. We go out along the green and then we can't go backwards along the green. It doesn't go down. And then 3, as time goes on, the green becomes inconsequential because this one grows so much faster. So we end up going parallel or close to parallel. The further we go out in time, the more parallel it gets to this 3. So hopefully I've addressed all 3 of those things. With these positive exponents, if I go to negative exponents, I get an inverted relationship. You could almost think about doing negatives with the graphs that I had on the TI there, and then what would it do? It would just flip those graphs over the y-axis, so it's the total opposite. So this is an example of one for which we have negatives, and you could go through the same analysis. I'm not going to do it in this video. The hardest thing with these, when these vectors, 1, -1, 1, -2, they're really close to each other, is getting this to come in parallel to the -2 first, and then going parallel to the -1. But hopefully this helps you out with some phase plots and clarifies some things and makes you think about what these things are representative of.